Hi guys, this is a little screencast that's going to be considering long-term chronic adaptations of the body to exercise. By the end of this session, you guys will be able to describe and explain the long-term adaptations of the cardiovascular system, the respiratory system, the musculoskeletal system and the energy systems to exercise. Now, this PowerPoint is going to directly help you with P3, P4 and M2. So for P3, you need to describe the long-term effects of exercise on the musculoskeletal system, and also the cardiovascular system, energy systems and respiratory system. Once again, there's a merit criteria attached to this, so whenever you're explaining any of the long-term effects of any of those systems, you've got to remember to put sporting examples in there, otherwise you won't achieve the merit criteria. What I suggest you do is, for cardiovascular, you describe all the key terms and then at the end create a separate page or a separate section, subheading, where you give me some examples and incorporate each key term into that. So, first and foremost, we've got cardiovascular adaptations. Now, there's 9 adaptations that occur when we participate in long-term exercise. So long-term exercise is defined as exercise that goes on for longer than about 4 to 6 weeks. So some of the adaptations that occur are cardiac hypertrophy, increased stroke volume, increased cardiac output, decreased resting heart rate, decreased blood pressure, capillarization, increase in blood volume, decrease in recovery time and increase in aerobic fitness. The first thing I need to make you aware of is that all of these are interconnected, so you'll hear me repeat myself a few times and elaborate on a few things in similar ways to one another. So, cardiac hypertrophy. Now this is quite simply when the muscle in the heart, the myocardium, when it's worked, when it's exercising, it actually becomes bigger and stronger. Now what this does is it creates a more efficient heart, and it helps to expel more blood with every beat as well, which is the next key term, increased stroke volume. So increased stroke volume, quite simply, is the amount of volume of blood that is pumped out of the heart by each ventricle during one contraction. So what that means is, if the muscle wall of the heart is much stronger, as we talked about muscular hypertrophy, every time it pumps it can squeeze more blood out, which increases the amount of stroke volume, the amount of blood that can be expelled out of the heart with each beat. When you have an increase in stroke volume, you also have an increase in cardiac output. Cardiac output quite simply refers to the volume of blood ejected from the ventricle in 1 minute. It's a combination of heart rate times stroke volume, so we work out how much is expelled with every beat, and we times that by how many times our heart beats. The increase in stroke volume causes an increase in cardiac output, and vice versa. The next point is a decrease in heart rate, resting heart rate. Because there's an increase in cardiac hypertrophy and stroke volume and cardiac output, the heart's able to expel a greater amount of blood, exactly what I said earlier. This means that the heart doesn't need to beat as much. This makes the heart much more efficient and reduces heart rate. The next key term is capillarization. Now, if we think of capillarization, we're talking directly about the capillaries that are attached to the arteries and veins, venules and arterioles. Capillarization is quite simply the increase or development of capillaries. So that might mean the increase in diameter or the activation of any dormant capillaries, any ones that haven't been used for some time. Because the body fundamentally only needs or uses what it needs. So if muscles don't need an excessive amount of blood, it actually closes off capillaries and redirects the blood elsewhere. We learnt about vascular shunting. So when we start to train, when we start to exercise, any dormant capillaries that haven't been used actually become reactivated, so blood can flow freely to the working muscles. When we have an increase in capillarization, an increase in diameter of the capillaries, and also an increase in vasodilation of the arterioles, venules, arteries and veins, we get a decrease in blood pressure. If you think about it, it's exactly the same if you think about plumbing. If you have a pipe that's a certain size, if you put a bigger pipe into it, then more water flows through it. It's exactly the same with our body. So as we start to exercise, our capillaries, arteries, veins, venules, the diameter increases, and that just allows us to pass more blood through. So because more blood's going through and there's a larger area for blood to go into, there's a decrease in overall blood pressure within the arteries and veins. Good thing about the body is that it recognises when adaptations are occurring. So if we do have a decrease in blood pressure, that means that we're working quite efficiently. But the body isn't just resting at that. It starts to think, well, actually, if there's a decrease in blood pressure, but there's an increase in demand for blood, we can actually create more blood now, and we can increase that off and push it further. So because of the increased supply for blood that exists in the body, it actually creates more blood. This is because the body recognises there's been a reduction in blood pressure because of a training adaptation, and it responds by producing more blood because it knows that an increase in blood will allow more haemoglobin to carry O2 and CO2 around the body. If there's more blood in the body, with a lower blood pressure and more efficient heart, there is an increase in aerobic fitness. This fundamentally means the body is able to take in more oxygen and expel more CO2 whilst becoming more efficient at removing and recycling waste products. If you think about it, if you haven't exercised for some time and our heart hasn't pushed itself at its limits, which has caused an increase in strain to the cardiovascular system, then if you did start to exercise after having been sedentary for any period of time, you have a massive increase in heart rate and you become out of breath really quickly and sweaty, and it takes you a long time to recover. As we start to do long-term training, then this changes and it improves things. So, as we were mentioning, this leads to a decrease in recovery time. So the cardiovascular adaptations that occur combine to enable the body to reduce the amount of time required for it to recover. This is determined fundamentally by the body's ability to move blood around its system, efficiently transporting oxygen to replace oxygen debt in muscle tissue, whilst quickly getting rid of CO2, lactic acid and any other waste products. So if we do some sort of long-term exercise for 6 weeks and above, then our resting time, our recovery time becomes shorter. So then we could do a high intensity bout of exercise a lot sooner after exercising. There are 4 respiratory adaptations that we need to talk about. We've got an increase in vital capacity, an increase in minute ventilation, increase in strength of respiratory muscles, an increase in oxygen diffusion rates. And I've put these in order so that you can follow it quite easily. So, first and foremost, increase in strength in respiratory muscles. Quite simply, when we exercise, we need to breathe quicker and deeper. This action causes the muscles we use to become stronger, which allows us to take in and expel more air. So there's a number of different muscles that are used. We've got the internal and external intercostal muscles. We've got the diaphragm. We've got even the sternocleidomastoid up in the neck and the scalenes. And the pectoralis minor also helps with breathing. And all of those, including abdominals, all act to increase our cavity of our thoracic cavity. So if we start to exercise and continue to exercise for long periods of time, our lungs and our muscles are going to be able to stretch and become stronger and draw in more air, therefore taking in more oxygen, expel more air, getting rid of carbon dioxide. We already touched on vital capacity earlier on when we were doing anatomy and physiology, but vital capacity fundamentally is a combination of inspiratory reserve volume, expiratory reserve volume, and tidal volume, our normal breathing volume rate. A combination of all those things, we found out earlier that vital capacity is usually around 4,800 mils for an average man, and slightly less for an average female. However, if we start to exercise, we get an increase in vital capacity because our muscles are becoming stronger and because we get a bigger surface area, alveoli, things like that, all combine to increase the capacity of an athlete, which once again helps an athlete to take in more oxygen and get rid of more CO2. This leads to a bigger minute ventilation. So exactly what it says on the tin. Minute ventilation is the volume of gas inhaled or exhaled from a person's lungs per minute. It's calculated by taking breathing rate, how many times we breathe, and timesing that by tidal volume or vital capacity, depending on how intense the exercise is. The more air we can take in and expel, the more O2 and CO2 diffusion can occur, which leads us to oxygen diffusion rates. So we know that oxygen and carbon dioxide move from where there is a large concentration to where there's a low concentration. This movement is called diffusion. Oxygen diffuses from the alveoli into the blood in the capillaries. Similarly, carbon dioxide moves from the blood out of the capillaries into the alveoli to be exhaled The increase in oxygen diffusion is attributed to an increase in minute ventilation and vital capacity, and once again it all links into the increase in strength of respiratory muscles. There are a number of musculoskeletal adaptations that we need to consider. Muscle hypertrophy, increase in tendon strength, increase in myoglobin stores, increase in number of mitochondria, storage of glycogen and fat, muscle strength, tolerance to lactic acid, increase in bone calcium stores, increase stretch of ligaments, an increase in the thickness of our cartilage, and the production of synovial fluid, which all of them need to be addressed. So, we know a little bit about muscle hypertrophy from when we did the muscular system in anatomy and physiology, but quite simply, muscular hypertrophy is just the increase in size in the muscle as a response to training. It's a growth in size of all its component cells. There's two different types of hypertrophy, which is probably a new bit of information to you. There's sarcoplasmic hypertrophy, which focuses on things like increase in muscle glycogen storage, an increase in something called a sarcoplasmic reticulum, and the network that supports the muscle cells. The one that we're most common with is the second type of hypertrophy, which is myofibrillar hypertrophy, and this is when the actual myofibrils and muscle fibres become bigger, and that's what we historically link to muscle hypertrophy. But if the muscles are going to become big and stronger and there's more surface area, then there's going to be more myoglobin stores. Now, myoglobin stores, quite simply, is very similar to hemoglobin in terms of it stores oxygen. However, it stores it within the muscle fibre. So the more muscle there is, the more myoglobin there is. Therefore, the more oxygen can be stored within muscles. So when we start to exercise, we have a supply of oxygen that's ready just to be activated and used straight away. As muscle increases, we also have an increase in glycogen stores and also fat stores. So when muscle hypertrophy occurs, muscles become bigger. The increase in size means that there's more space for glycogen to be stored inside the muscle. This helps because there's a greater supply of glycogen close to the mitochondria, which can quickly synthesize it for ATP production. The same can be said about fat, but where fat differs is in its storage. Fat is stored in adipose tissue, which surrounds muscle. The closer the adipose tissue is to mitochondria, the faster it can be synthesized into ATP. So as we start to exercise and do continued exercise, yes, traditionally fat stores go down, but the amount of fat that surrounds key areas might remain the same. It might be the last thing that gets broken down. And the reason for that is fat surrounds muscle because it provides fat as a source to create ATP. Now, mitochondria, I'm not sure if you remember from when we did the energy systems, mitochondria is the powerhouse of the cell. It's basically the cell that creates all of the adenosine triphosphate, either inside its matrix or just on its outer membrane. Mitochondria creates ATP by resynthesizing things like proteins, fats and carbs. As we continue with long-term exercise, the body actually creates more mitochondria and excites existing mitochondria that might have laid dormant. So the more mitochondria there are, the more ATP there is, and the more energy that our muscles can use for exercise. All of these combined create a muscle increase in muscle strength and also tolerance to lactic acid. So I talked to you a little bit about the two different types of hypertrophy earlier. We talked about myofibrillar hypertrophy, which is when the muscle fibres become bigger, but also the most important thing for this is the sarcoplasmic hypertrophy. So just to recap, this is the enlarging of all supporting structures that surround muscle. The sarcoplasmic reticulum is one part of this, and when it grows in response to training, it creates a drainage network that enables carbon dioxide and lactic acid to be removed from the muscle much quicker, limiting the acidic effect it has on muscle fibres. The secondary job that it does is it increases the amount of calcium that can be released into the muscle, so it also increases the strength of muscular contraction. Whenever we start to exercise for long term, over six weeks and more, we get an increase in tendon strength. Tendons are made up of strong connective tissue designed to withstand large amounts of tension. They attach to bones and joints. They connect to a muscle, connect muscle to the bone. So long-term exercise causes an increase in tendon density, which in turn increases tendon strength and just prevents any injuries from occurring, or tries to prevent any injuries from occurring. We also get an increased stretch of ligament and also strength of ligament. Bones are held together with non-elastic avascular straps or cords, which are called ligaments. So avascular just means that it doesn't have a very good supply of blood or oxygen to it. When exposed to long-term exercise, ligaments become firstly stronger and more resistant to injury, and then secondly they become more pliable, which means they can stretch further. Because ligaments have a low or very poor blood supply, any adaptations are very slow to develop. Another skeletal adaptation is the thickness of a cartilage. So cartilage is a flexible but strong supportive connective tissue. Unlike bone and all other connective tissue types, cartilage is avascular, which means it lacks with blood vessels and therefore it lacks with oxygen getting to it. As we participate in long-term exercise, the shock absorption qualities of cartilage has to increase. It does this by forming more cartilage from cells called chondroblasts. When a new cartilage is created and added to the existing cartilage, the gliding and shock absorption qualities help to reduce friction within the joint capsule, which reduces wear and tear. We also become more able to produce synovial fluid. The bones and joints have little or no blood supply, so in order to keep the joints healthy and to stop cartilage from dying out and keep cartilage lubricated and nourished, the joints produce an oil-like substance called synovial fluid. Synovial fluid is produced by the synovial membrane within a joint and is a short-term or acute response to exercise, meaning that during short-term activity, a lot of synovial fluid is released to reduce any sort of friction. Long-term exercise enables the synovial membrane to become stronger, bigger, and to create more synovial fluid, which continues to protect the articulating surfaces and keep the joint as healthy as possible. The last musculoskeletal adaptation is an increase in bone calcium stores. Our bones are strengthened as a result of the stress that's placed on them by exercise. So quite simply, the more exercise we do, the stronger the bones become. Exercise causes an increase in mineral stores, which help provide more space for calcium and other essential minerals to be stored. The increase of calcium in the bones helps to strengthen it, and it also provides a greater source of calcium, which is an essential component of muscular contraction. The last two key terms that we need to know for these long-term adaptations is aerobic and anaerobic enzymes, or an increase in aerobic and anaerobic enzymes, and also an increase in the use of fats as an energy source. So, aerobic and anaerobic enzymes fundamentally produce energy by making ATP. Whenever you see the word enzymes, or if you saw the word or the letters ACE at the end of something, ATP, ACE, for example, then you know it's an enzyme. It's something that creates it. It's like a kind of a factory. It's a mechanical aspect of our cells. So by increasing enzymes, it means more ATP is produced. Therefore, this gives you more energy to keep going. If you're exercising for a long time, you'll need more energy, or you won't be able to carry on for very long. Anaerobic enzymes increase to control the anaerobic phase of glucose breakdown. This means more energy will be produced. An increase in aerobic enzymes means there is an increase in mitochondria. This means that more energy will be supplied to the athletes. The increase in enzymes means the athlete will be able to work at a higher intensity if using anaerobic enzymes, or work for longer using aerobic enzymes. So quite simply, anaerobic enzymes help you to produce more explosive energy, where aerobic enzymes help you to produce more lower level long-term energy. And the last key term, using fats as a source of energy. So the more exercise we do, the longer we do it for, the more likely our body is to start to use fat to create ATP. Fats are unfortunately used as a last resort for energy, and are used in sports such as marathon running, things like that. Fats are stored in very large molecules, so they need to be broken down, and it takes a long time to break them down. There's quite a few chemical reactions. After exercising for a long period of time, fat oxidation increases, so it's able to break down the fats. Fats provide more ATP than carbohydrates, however they do take longer to oxidise because there's many more chemical reactions. Fats are definitely the best source of energy and provide the body with most ATP molecules. Right guys, so that's a little introduction into the different long-term adaptations that occur within the body. I hope that it's been useful for you, and I hope this screencasting method's been good for you as well.